Here's another question about a stained glass window again. Suppose you have a square window of side length 2, which is divided into 3 panes as follows. The midpoint of one side is connected to one of the opposite corners, and the other opposite corner is connected perpendicularly to that line. What is the area of the smaller of the 2 triangles formed? This would be the smaller of the 2 triangles. And so now we're asking for the area of this. I want to say on this question, because everything is so nice, because we have a square, there is actually a way to do this, which I would say is possible, but I would call painful, which I'll mention first, which involves first drawing this line here, and then saying that if the side length of the square is 2, then this is 2, this is 1, this is 1, this is 2, and then you can even calculate, for example, this length to be the square root of 5. And from there, you can start to play with an area argument, which means that the whole thing altogether was an area of 4, subtract off an area of 1, another area of 1. This has an area of 2, and then you can use a half base times height to figure out this length, followed by the Pythagorean theorem to get that length, and then you can finish. I don't want to do it that way, but I did want to say it's possible because it's important to know when you can solve a question in one way or another. And if that's the only way you thought of, it's good to just be able to do it with that way. The method I want to use instead is actually hinted at by the title. There was another problem in this simulated AMC10 where it was called stained glass, and the key idea there was similar triangles. Actually here, there are also similar triangles. If I clear this off, let me do what I usually do, which is to mark things that are the same. The first one that I'm going to mark that's the same is that these 2 angles are the same because I have 2 parallel lines and 1 line cutting across. I'm also going to say that I know that there's a right angle here because this is a square. At this point, I actually have these 2 triangles, which are both with a red and with a right angle. And so what that means is that their other angle, which I'll mark with 2 blue lines, their other angle has equal measure. So that means that these 2 triangles are similar. But I know the sides. I know, for example, that this one has a side length 2 and this has a side length 1. And as I mentioned before, because of the Pythagorean theorem, this long side is the square root of 5. On the other similar triangle, I have that this long side, the hypotenuse, has a length of 2. So what that means is that if I want to turn myself from this triangle into that triangle, I have to multiply by a scale factor of 2 divided by square root of 5. Just to do a quick mental check, that's less than 1, because square root of 4 is 2. It's good that that's less than 1, because I want to know the area of the smaller of the 2 triangles. But now I'm actually almost done, because the area of this triangle is easy with 2 and 1. The area of this triangle is simply 2 times 1 divided by 2, or 1. That's the area here. So that means that the area of this other one is the old area times the square of the ratio I multiply by. 1 times the square of 2 over root 5 is simply 4 over 5. That's actually all there is to it. One thing I want to emphasize, whenever you have rectangles and lots of perpendicular lines and lots of parallel lines, first chasing around to see what angles are the same and then using similar triangles can save you a lot of time.